This conference will now be recorded.
Hello everyone. So after discussing 2 to 3 problems, we'll start today's topic, which is electromagnetic spectrum, then particle nature, dual behavior of light, Planck's theory, line spectrum, absorption spectrum, all these things we'll discuss. So here the problem is saying it is based on Thomson model and also Rutherford's gold foil experiment. So these two we have discussed in the last class. So it is saying that if the Thomson model of the atom was correct, then the result of Rutherford's gold foiled experiment would have been. Try to understand it thoroughly. Thomson model, it was built before Rutherford's gold foiled experiment. Historical point of view, if we see. That means there is obviously some modification in Rutherford's experiment compared to Thomson model. It is a better version of atomic model. Now the question is asking that if Thomson model was correct, because it is not absolutely correct, there is obviously some demerits, some defects are there. But suppose if it is correct, based on that assumption, what should be the result of Rutherford's gold foil experiment? Okay, here we have 4th statement, and among these statement, we have to choose the correct option. So rest of the 3 that will be not correct. Now to answer this, obviously we have to have proper idea about the Thomson model. So according to this model, look at this here. According to this model, it says that there is spherical cloud of positive charge throughout the atom. That is, if you consider the total environment of atom, then there is spherical cloud of positive charge, and as if these negative charge particles, which are basically electrons, as if they are swimming in the positively charged sea. Okay, so as if it is a sea of positive charge and electrons are swimming in this homogeneous cloud of positive charge. So if this is the correct model, now based on that we have to understand what should be the observation of Rutherford's gold foil experiment. In Rutherford's gold foil experiment, there is some use of alpha particles, which is nothing but helium-2 plus particles. So these alpha particles, they are basically positive. So when these alpha particles, they are moving towards this atom, obviously, as it is itself positive, there will be repulsion between the positive charge already present in the atom and the positive charge of this alpha particle. So because of this repulsion, there will be some deflection. Now in Rutherford's actual experiment, what we have seen, that the positive charge, it is centralized in the small portion in the center of the atom, which is basically the nucleus. It is not that the positive charge is spreading throughout the atom. No, it is not that. It is concentrated in the small region, which is basically this nucleus. But according to Thomson model, it is spreaded all over the atoms. Fine. So that is why now the result that you have already seen in Rutherford's gold foil experiment, it will not be same, because here these two models are completely different. Now come to the statement one by one. The first statement is saying that all the alpha particles pass through the gold foil without decrease in speed. So they will pass without decrease in speed. That means they can easily pass throughout this, but that is possible only if most of the spaces in the atomic model it is vacant. But actually that is not the case in case of Thomson. So you have to choose the observation based on Thomson model, not the actual Rutherford's model. So that is why this statement we cannot consider as correct option, because alpha particles cannot pass through the gold foil without decrease in speed. That is all the alpha particles, because this positive charge, it is spreading all over the atom's atmosphere. So that is why this statement cannot be true, because there will be positive charge repulsion. Second statement is saying alpha particles are deflected over a wide range of angles. So deflected over a wide range of angles, that means when they are going straight, and then there is a deflection wide range. And the third statement is saying all alpha particles get bounced back by 180 degree. That means it is going and then it is coming back. So it is 180 degree as if like this. And it is deflected by a wide range of angles. If you consider this observation, it is going straight and then there is some deflection. So this angle is also very large angle. That means there will be some positive charge with which there is repulsion occurring. And the last statement is saying that alpha particles pass through the gold foil deflected by small angle and with reduced speed. That means now also there is deflection, but the angle is not very high as it is mentioned in statement 2. And also there is reduction in speed. This is also mentioned. Now, if we consider the logic of Thomson model, here protons are not centered that you have seen in case of Rutherford's gold foil experiment. Here it is diffused throughout the whole atomic model. And as a result, the alpha particles will deviate by very small angle, because large angle deviation is only possible when the positive charge, it is directly confronting all the positive charge centered in a small place. But all the positive charge, they are not centered in a small place. They are diffused throughout the atomic model, throughout the atom. So that is why there will be positive charge repulsion, but the angle will not be very high. The reason is here positive charge is not centralized in a small part. It is diffused in the whole region. So that is why there will be deviation, but it will be small angle. That is mentioned in the last statement because of repulsion with the proton. And also speed will decrease. That has to be because there is some repulsion with the same charge. So keeping all these points in mind, here correct option should be the last option. Fine. Next question. Yellow light emitted from sodium lamp have wavelength 580 nanometer. So here wavelength is given, and wavelength it is, we express it by lambda. So lambda is given 580 nanometer. We have to calculate frequency and wave number. Frequency is denoted by this type of nu sign, and wave number that is denoted by nu bar. So lambda is basically how it is related to nu, and how it is related to nu bar. If you know that formula, you can easily answer this question. Here given is wavelength, which is 580 nanometer, and if you convert it from nanometer to meter, it should be multiplied by 10 to the power minus 9. Though it is not mentioned in the question that in which unit you have to express it, but better you can you understand all the conversion of units, so that if it is mentioned clearly, you can solve it. So C, which is velocity of light, 3 into 10 to the power 8 meter per second, and this is the formula. How nu and lambda are related to each other. Basically, if you multiply these two, that is equal to C. So you can say that frequency is basically, it is C by nu. Okay, so that is why, sorry, it is, yes, lambda by C. So first we'll place the value of lambda, which is 580 into 10 to the power minus 9. So this we have already seen here, right? And what is the velocity of light? That also we have mentioned, which is 3 into 10 to the power 8 meter per second. Fine. And if you do this calculation, you will get 5.5 into 10 to the power 14 second inverse. Okay. So frequency unit, it is always in second inverse unit. Fine. That means here meter, that should be cancelled out, and second inverse, that will be remaining. Sorry, it is. c by lambda. So it should be 3 into 10 to the power 8 divided by 580 10 to the power minus 9. So here unit is meter per second and here unit is meter. So meter will be cancelled, second inverse will be remaining, and here the power is 8, here minus 9, and 3 by 580, this calculation you have to do, but finally it will be 10 to the power 40. So it is very high power of 10, right? So meter cancel, second inverse. So in this way you can calculate frequency, and if it is wave number, that is the next one, which is basically inverse of lambda, or it can also be expressed as nu bar. So it is simple, 1 by 580 into 10 to the power minus 9, and that will give you 1.7 into 10 to the power 6 meter inverse. So that will also be in meter because we have already converted to meter. If you have not converted, it will be simply 1 by 580. Okay, so be very careful in which unit it is asking. That is the final answer. Here it is not clearly mentioned, but sometimes it may be mentioned also. Next question. Calculate wavelength, frequency, and wave number of wave whose time period is given. Now time period is given. What is time period? That we have to understand. Look at the unit of time period that is given. Here the unit is S. That means it is inverse of frequency, that is second inverse. Now the relationship of between wavelength and time period, frequency and time period, and wave number of time period, if it is clear, then we can easily solve this question. So time period, it is given in second unit. So it is inverse of frequency, because which is clear from the unit. So frequency, we know it is second inverse unit, that is time inverse unit. So frequency must be 1 by t, then only the unit of frequency will be second inverse. So 1 by 2 into 10 to the power minus 10. And also try to remember the definition of frequency. So per unit time, it is through a common point, how many waves are going per unit time, that is actually the frequency. And per unit time, when I'm saying, it is basically per second, not just any unit. It is not per hour or per minute, it is per second only. So reverse of 2 into 10 to the power minus 10, and it will be 0.5 into 10 to the power 10. And remember, whenever you are doing this calculation, just check once you have obtained your answer that whether it is having very high number, because always if you look at any value of frequency in any problem or any book, you will always see that the power of 10, it is very high, it is not in negative. Okay, because number of waves through a common point, which is it is passing through per second, obviously it cannot be something 10 to the power minus power. That is not possible. It will always be very high number. So that is why you will see it is mostly 10 to the power any power which is in positive. So the total number is very high. So 10 to the power 10 second inverse. And once you know the frequency, you can easily calculate lambda from the same relationship we have used in the previous problem. So wavelength will be c by nu. So nu value we have just calculated, 3 into 10 to the power 8, that is the velocity of light, and ultimately we get 6 into 10 to the power minus 1 meter or 0.6 meter. And wave number, it is inverse of lambda. So 6 into 10 to the power minus 1, if you take inverse of it, you will get, or you can write it as 0.6. If you take reverse of it, it will be approximately 16.667. So the first topic in today's class, electromagnetic spectrum. What is wavelength? What is wave? What is frequency? What is amplitude? All these things we have seen in the last class. So from this picture you can understand, as we are moving from left to right, there is increase in wavelength. And wavelength, how we will understand? Very easy. Just choose any 2 points in the crest or troughs. Anything you can do. You can also choose here. So this distance that will give you the wavelength. But if you look at the left hand side, just choose any of these two. Here you can easily understand this length is very short. That means wavelength is very less here. And when wavelength is less, as it is inversely related to energy, energy will increase as you move towards left side, and right side it will decrease. So this is the relationship. Now if we see the actual electromagnetic spectrum, here in the upper part wavelength is mentioned in meter unit, in the lower part it is given in terms of frequency. We know when wavelength is increasing, frequency will decrease. So that is why, see here wavelength is 10 to the power 3, the last value, but here it is, if you move towards the same line, if you move through, it will be 10 to the power 5. That means in terms of frequency it is becoming high and high as you move towards left hand side, because energy is increasing towards left hand side and frequency is also increasing towards left hand side. See, 10 to the power 20, here it is 10 to the power 4, but if you look at the wavelength scale, it is 10 to the power minus 11, it is 10 to the power 3. Now in this range there are different regions that you can see. So the high energy region, that is gamma rays, the range is already given. Then the next range between these two values, it is X-ray, then ultraviolet ray, in short we call it UV, and then there is visible. So this small part which is between infrared and ultraviolet, this small part if we enlarge, you will see it is basically the visible part. And then there is microwave and radio. Fine. So in the visible part, just remember this value. This is the low energy region towards the red end, and the blue end, that is the high energy region. 400 nanometer and 750 nanometer. So these two are the two extreme for the visible range in terms of wavelength unit. So 750 and 400. Obviously, you can understand this side is high energy. This side is low energy. Fine. So only if the frequency and wavelength of the wave is in this region, that is this region, then only you can see some color. Otherwise, our eye will not be able to perceive the color. The electromagnetic spectrum can be defined as the range of all types of electromagnetic radiation. Okay, and all electromagnetic waves, there is some common property, and that is they move with same speed as light when it is vacuum, and that speed we know, speed of light 3 × 10⁸ meter per second. But wavelength, frequency, energy of all these different types of electromagnetic waves, it will vary, which is clear from this diagram. Fine. Particle nature of electromagnetic radiation. Once we know electromagnetic radiation, now there are some experimental phenomena. For example, here it is mentioned diffraction phenomena, interference phenomena. These two phenomena you can explain if you consider the wave nature of electromagnetic radiation. But there are some phenomena which you cannot explain if you consider only the wave nature of electromagnetic radiation. That means there will be some different types of nature also for electromagnetic radiation. Now, until now, we know that it is having some wavelength property. So that is why we are talking about wavelength, frequency, like this. But that is beside wave nature, there is also some other type of nature, and we will focus on that. But before going to that point, just let's have a primary idea what is diffraction and interference. These two phenomena you have seen it in day-to-day life. It is not something new. So what is diffraction? Diffraction is basically the phenomena which occurs for all the waves, describes the event of waves encountering an obstacle and the consequential bending along the object. So here you can see these two waves, they are moving smoothly, but once they are facing some obstacle, so here there is some obstacle. Sorry, it is you can see there are two openings. So these two are the two openings. This is one opening, this is another opening. But rest of the part, there is some obstacle. which is shown here by this vertical black line. So they cannot pass through that vertical line. You can also consider any water stream or pond where there is smooth wave of water waves you can see. But suppose there is some obstacle, and in this obstacle, if there is some opening, now the waves, they will be moving in this way. So that is known as diffraction. They are encountering some obstacle, and then as a consequence, there is bending around that object. So here you can understand, before this, that is in the left hand side of the obstacle, there is a wave, they are smoothly moving. But after this obstacle, we can see some diffraction. So these phenomena you can explain if you consider the wave nature of electromagnetic radiation. And what is interference? Interference is, suppose you have two waves, waves X and wave Y. If you add these two, there is a plus sign. The resultant wave, now look at this, it is in pink color, it is constructive, because now if you add these two, see here, this amplitude and this amplitude, they are just face to face. It is not that like in the second picture. In the second picture here you can see the maxima, but the maxima for the second wave, for the green wave, it is not just below it. It is shifting towards right hand side. So that is why it is not straight. So that is why it is destructive, because where you are seeing this maxima here, it is not the maximum we are having for the second wave. So as if it will cancel each other. So that is, it is destructive. So it can be constructive, it can be destructive. So as a definition, we can say that when two waves are meeting, then if we are adding them together, basically they add together. They add to each other and they form a resulting wave. Now this resulting wave, whether it will be constructive or destructive, that depends on how they are approaching each other, which is clear from this picture. Okay, so this phenomena is known as interference, and that also can be described if you consider wave nature of electromagnetic radiation. But there are some phenomena which we cannot describe based on wave nature. And what are those phenomena? The first one is black body radiation. Now the second one is photoelectric effect. So these two will be discussed in detail because that is present in the syllabus. There is another phenomenon also, which is variation of heat capacity of solid as a function of temperature. But we are not going into the details. Only the first two will be discussed in detail. So next is black body. So black body radiation, first see, you have to understand these four phenomena: emission, transmission, reflection, and absorption. So emission of light, so when it is moving through some, or electromagnetic radiation moving through some medium and it is completely emerging out, so it is emission. Then transmission, sorry, I'm talking about that, suppose there is some object and some waves it is emitting, so that is actually emission. Transmission is if it is already moving and then it is facing some medium, but even after facing the medium it is coming out, then it is transmission. Then reflection, so when the wave is going on and electromagnetic radiation is going on and then it is reflected at this point, then it is changing its direction. This is known as reflection. Try to understand the difference of these four phenomena. And then there is absorption. So when it is absorption, now when it is facing this medium, it is completely absorbed in the medium. So that is these four different phenomena. Now, before going to black body radiation, we have to understand what is black body. So here we will try to understand what is black body. The ideal body which emit and absorb all the frequencies, that is known as black body. That means, just look at the first phenomena, emission. So there will be complete emission of all the frequencies, and also it can absorb all the frequencies. So emission and absorption, as if these two are reverse phenomena, but it can, that is ideal black body will be that object which can emit all the frequencies, and also it can absorb all the frequencies. Then that body is known as black body, and the radiation emitted by such body is known as black body radiation. Now it neither reflects, we know what is reflection, neither it transmit, we know what is transmission. So these two processes are not occurring, only complete emission, complete absorption. It neither reflects nor transmit any of these incident radiation, and that is why it is appearing black. Whatever is the color of the incident radiation, that doesn't matter, because of this complete emission and absorption. Now the black body radiation, if we see these experimental results, we are trying to explain it here in a very simple way. In the y-axis we have spectral radius. Sometimes you will see it is mentioned as flux, or it is mentioned as intensity. So it is basically intensity of the radiation. It can be mentioned in different names, but actually it is intensity. Okay, that is how many electromagnetic radiation or waves present. That is intensity. And here we have wavelength in the x-axis. Now look at this line. If you are following classical theory, which is shown here by the black line, that is according to that theory, our observation should be like this. As the black line, see, as we are moving from high wavelength towards lower wavelength. So this side is lower wavelength, that means high energy. Here energy is high, this side is energy is low. So when it is moving from high wavelength to low wavelength, that is towards lower energy, then this intensity, it is increasing and increasing, and it is in the infrared region, and it is going on like this. But actual what happens, that you can see in the other lines, that is the red line, the green line, and the blue line. So when it is, just consider any of these temperature, because these three are different temperature. Just choose any of these temperatures. Suppose I am choosing this 400 Kelvin temperature. So when temperature is fixed, first you have to fix the temperature, then only you can understand how the intensity it is changing with wavelength. That is how these two are related, because if temperature is not fixed, we cannot understand what is the relationship between this intensity and wave. So first you have to fix the temperature. Under that condition, just focus on this green line. If you are moving from high wavelength towards lower wavelength, first there is increase in the intensity, then it is reaching a maxima, which is at this point. If you draw a line, it is somewhere here. So at this particular wavelength, there is maximum intensity. But don't think if you further move towards low value of wavelength, it is not that it will increase. That is actually according to classical theory. That is where we simply consider the wave theory, classical theory. If you only consider that, the observation should be like this. It is increasing and increasing. There is no such maxima, and then there is again decrease. So actual observation is something like this. First there is increase, then it is reaching a maxima at this particular wavelength, and then there is again decrease. Okay. Now same type of observation you can also have if you choose some lower temperature, 300, and you can also see it is now reaching maxima, suppose at this point wavelength. If you choose some high temperature, suppose 500 Kelvin instead of 4,000, sorry, not 500, 5,000. So instead of choosing 4,000 or 3,000, if you choose very high temperature like 5,000, now you can see that the basic nature of the curve is same. First there is increase and then there is decrease. Or you can also think it in reverse order. Suppose you are moving from low wavelength to high wavelength, then also there is increase in intensity, and then there is again decrease in intensity. Now when it is 5,000 Kelvin, this is the maximum. If you draw a line, you will reach any wavelength somewhere here. So this is the observation. Now just forget about this intensity versus wavelength. Suppose if you are changing the temperature from 3,000 to 4,000 to 5,000, it is true that in all these three temperature, The basic nature of the curve is same. But what is the difference when you are increasing the temperature? The difference is now this maximum, this point, just focus on this point. Then here it is, this is the maximum peak point, and this is the peak point at 3000. Now, if I join all these 3 points, as if when you are moving from longer wavelength to lower wavelength, shorter wavelength basically, then the maximum that is shifting towards left hand side, which is clear from this yellow line. First it is somewhere here, then the next point, if you draw a line, it is here, and when it is very high temperature like 5000, now the maximum is here. So though it is very small difference, but still one thing is clear, that the maximum is shifting towards left hand side. So these are the important observation. And also see, in this particular wavelength range there is visible region. So the maximum that is the peak point, it may be in visible region or it may not be in the visible region, and that depends on what temperature you have chosen. So if you have chosen 3000 Kelvin, then the peak point, it is not in the visible region, it is in infrared region because it is here. Now if you have chosen 5000 or 4000, gradually it is in visible region. Fine. Now we will see all the points one by one. When an ideal black body is heated, it becomes first red hot or emits red colored light. You can consider any metal object. Suppose you are heating that, first there will be change in the color, it will be red hot. But if you further increase temperature, gradually the color will be moving from red to yellow and finally white. Now when it is moving from red to yellow to white, basically it is an indication that energy is increasing. That means it is moving towards shorter wavelength. As temperature is further increased, the color of the radiation emitted changes its color from red, yellow, white, and finally it becomes blue, which is the maximum energy it has reached. So energy and frequency or in terms of energy or frequency is relation with temperature. In this experiment it is directly related. So when you are increasing temperature, frequency is increased, or you can say energy is increased, which is clear from this color change. So this implies that wavelength of radiation emitted by the black body, it decreases with increase in temperature. So in terms of wavelength it is reverse relation, but in terms of energy or frequency it is direct relation with temperature. Now if you fix the temperature, we know how the temperature it is related to wavelength. But if you fix the temperature and try to understand the relationship between intensity of radiation, which is this spectral radiance in the y-axis. So at a given temperature, intensity of radiation, how it is related to wavelength. Intensity of radiation emitted first increases with the increase of wavelength, then reaches a maximum value at a given wavelength, and then it again start decreasing with further increase of wavelength, which is clear from this picture. And one more important point here, see, as I have drawn these, I have attached these 3 max points of these 3 lines and by this yellow line. So this is related to the last point. It says that as the temperature increases, maximum of these 3 curves, in this case we have only 3 curves, maximum of these 3 curves, it is shifting towards shorter wavelength. That means intensity where it will be, that also depends on temperature. Okay, so when temperature is very high, the intensity it is towards shorter wavelength compared to 4000 and 3000. So these are the observations. Now why these observations are important? Because it is denying the classical theory. Because at classical, if you only consider classical theory, then at 5000 Kelvin, the nature of the curve should be like this black line. As you are seeing here, it should be increasing like this, and there is increase and increasing. It is not having this type of nature. This type of nature is you are not getting if you consider classical theory. According to classical theory, it is only like this. It is increasing and increasing. But actually, this is not I should not give cross mark because this is the actual observation which we are getting, not this one. So in this way, it proves that if you simply consider wave nature or classical theory, you cannot explain black body radiation, right? So there must be something else behind wave theory, and that we have to now understand. And that is actually quantization of energy, which is basically Planck's theory. Scientists were not able to explain these observations that you have just seen in the previous slide with electromagnetic theory. So Planck now is giving some new theory. He was able, by the assumption that absorption and emission of radiation arises from oscillators. That is, you can consider in a simple way as if they are atoms that are present in the wall of black body. Now, when frequency of this oscillation is changed by interaction with the oscillator of electromagnetic radiation. So there is already some atoms present in that particular object in the walls of the black body, and when there is electromagnetic radiation, there is interaction with these new oscillators that are coming from electromagnetic radiation. So this theory says the radiation energy emitted or observed in the form of small packets of energy. So radiation energy emitted or absorbed. Okay. It is basically in the form of small packet or energy, and this small packet of energy that is known as quantum or proton, and it is not in continuous manner. So you can take this simple picture. Suppose you have this stair. So when you are going to through stair, this vertical part, you cannot place your foot, right? You can also consider this ball. When this ball is moving from a high region to this lower region, it can touch only these horizontal surfaces, not the vertical. So if you are also, if you are working, you can place your foot only in this part. So as if it is quantized, the vertical parts are not available. But there may be another way. Suppose there is no stair. So this ball now it is moving continuously as if it is rolling ball. Fine. So try to understand these two differences. So the second picture, that is basically if you consider simple the classical theory, or if you only consider wave theory, which is basically continuous. But this new theory, which is given by Plancks, because based on wave theory you cannot explain black body. So this new theory is basically quantization. So only some small packet of energy is available. You cannot have less than this packet or more than this packet. Yes, multiple of this packet is possible. Fine. So each of these place, suppose this is one packet, this is another packet, this is another packet. So you have to keep your foot here. On the ball, it has to touch this part. That means these packets are available, but you cannot have less than this or more than this. So that is, this concept is quantization. So there is some restriction. It is not continuous. In the second picture, you can see there is no restriction, but in the first picture, there is some restriction. So the restriction of any property to discrete values, as you are seeing in this case, that is, it is energy is available in the form of quantum or photon. This restriction is actually quantization. Energy of each photon is directly proportional to frequency of radiation. That already we know. So same type of relation, we know E is equal to h nu. That means h is constant. That means energy is directly proportional to frequency. And Planck's constant, it has this fixed value 6.626 10 to the power minus 34 joule into second. Sometimes it is also written as 6.63 instead of 6.626. So this is the relationship. But remember, the main difference with the previous classical theory is that now the energy is not continuous. It is available only in small packet. Calculate energy of 1 mole of photons. So in this problem you can see we have mentioned that photon. So now we know what is photon. So one photon means one small packet. We have to find energy of 1 mole of photons. That means Avogadro number of photons. Frequency is given. Energy unit, Hertz unit. Hertz is nothing but second inverse. So it can be expressed in Hz, that is Hertz, or it can be expressed as per second. So both are fine. 1 mole of photons, we have to find the corresponding energy. Frequency value is given. Energy of 1 photon we can easily calculate from this relation, h into nu, that you have just seen in the previous slide. So this is the value of Planck's constant h. Mostly you will see it will be given in the problem, but better if you can memorize it, it is always better. And this value is given in the problem. So if you multiply these two, second and second inverse, which is nothing but Hertz, it is same as second inverse. It will be cancelled. Now you are left in joule. So this is the energy of a single photon, but we need the energy of 1 mole of photon, and 1 mole of photon is Avogadro number of photons. So it is actually n, where n is the Avogadro number, 6.023 into 10 to the power 23 per mole. So this is the number of particles. It may be photon, it may be electron, it may be proton, anything. So in our case, it is Avogadro number of photons. So this number must be multiplied with this, which is basically h nu that we have just calculated, and this will give you 199.5 into 10 to the power 3 joule per mole. Now in the question it is not mentioned what should be the final unit. Sometimes you should carefully read the question whether it is asking the final answer in terms of joule or in terms of kilojoule. So if you are expressing in terms of joule per mole, it is 199.5 10 to the power 3. But the second one, it is basically kilojoule, because now we have removed this 10 to the power 3 term. So in terms of kilojoule, if it is asking the answer, then the answer should be 199.5. Second problem. We have a 200-watt bulb. It emits monochromatic light having wavelength 400 nanometer. Calculate number of photons emitted per second by the bulb. Now we are seeing something new here, which is watt. So the unit of watt, what it means actually. Watt is basically unit of power. And power, how it is related to energy. So when I'm saying it is 200 watt, it means basically 200 joule per second. So energy per unit time, that is actually watt. That is joule per second, it is watt. Or you can say power is energy per unit time. So in this case, power is expressed in watt unit, energy is joule, and it is per second. So 200 watt means in 1 second we are getting 200 joule. This information we can get when it is mentioned it is 200 watt bulb. Lambda is 400 nanometer, but you have to convert from nanometer to meter because it is the energy is in joule. So you cannot use nanometer. Both should be in SI. So 400 nanometer, if you multiply it 10 to the minus 9, it will be converted to SI unit. Now you know what is energy, which is 200 joule. Fine. And keeping this aside, now we will calculate what is the energy of one single photon. So we know E is equal to h nu, but we do not know what is nu. So that is why we have to convert nu to C by lambda. So h into nu, that is also equal to hc by lambda, because nu is equal to C by lambda. So that is why we can place hc by lambda. Now we know what is h, 6.62 10 to the minus 34, Planck's constant. C is the velocity of light, and lambda, that is already given. So this is the energy for one photon. But we have 4.969 10 to the minus 19 joule. But we have available energy 200 joule. So if you divide this energy for a single photon, which is 4.969 into 10 to the minus 19, if you divide 200 by this energy term, so this is the total energy available, and this is the energy of one photon, and we need to find out what is the number of photons emitted per second. So per second energy available 200 joule. So that is why Finally, if you want to get number of photons, you have to do this final calculation, which is energy in 1 second, and this is the energy of 1 photon. So if you divide this, you will get the number of photons emitted per second. So answer is 4.026, 024 into 10 to the power 20 number of photons emitted per second. So this chapter, you will find many numericals type of question that is very common. So if we practice this more and more, it is better. A source of monochromatic radiation of wavelength, monochromatic means single wave, 400 nanometer provides 1000 joule of energy in 10 seconds. So in 10 seconds you can get this amount of energy. So you can say it is as if 1000, it will be, if you divide it by 10, you can get the power also. When this radiation falls on the surface of sodium metal, then this number of electrons are ejected per second. So this radiation is falling on the metal surface, and we know in metal surface they can easily donate electrons. So electrons will be now ejected, and when this radiation falls, x into 10 to the power 20 number of electrons ejected per second. Now if we do consider this assumption that wavelength 400 nanometer, it is just sufficient for ejection of electron from the surface of sodium metal, we have to find the value of x. So whatever will be our answer, we have to write it in this format, and then we have to compare, and in this way we can find what is the value of x. Now this last assumption, as it is saying that 400 nanometer is just sufficient for ejection of electron, that means the monochromatic radiation that we are using, that will be able to eject electron from the surface of metal. So here total energy, if we consider per second, because 1000 joule is for 10 seconds, but if you want to know what is per second, then because why we are focusing on per second, because ultimately the question is asking x into 10 to the power 20 electrons ejected per second, and you have to find the answer of x. So you should know what is the energy per second, not in 10 seconds. So that is why you have to do this calculation. 100 joule, that is the energy per second. Now energy required for ejection of one electron, that you can get from this relation. Remember in the last problem also we have done the same calculation, Hc by lambda, which is equal to energy. So whenever lambda is mentioned, you have to use this equation. If frequency is mentioned, you can use equal to h. Now putting the value of h, which is this one, this is c, this is h, and this is lambda. Now you can do this calculation, or you cannot do this, you can do the final calculation together. But if I am doing this, it will be 4.97 10 to the power minus 90. So this is the energy required to eject electron. 4.97 into 10 to the power minus 19 joule. Now in our case, we have already seen that per second energy is 100 joule. So number of electrons ejected per second. Now we have to divide 100. You can find some similarity with the previous problem also. Now we are dividing 100 by this amount, which is we have already calculated, and this is actually equal to 4.97 10 to the power minus 90. So if we do this, finally we will get the value. Actually you can get in different forms. Here it is mentioned like this, but first you can get it like this, 20.12 into 10 to the power 19. But if we have to arrange it in this format, x into 10 to the power 20. Okay, so x must be some integer. You cannot keep it 20 because this x value, it must be between 1 and 10. Okay, so that is why it cannot be 20. So the value of x cannot be 20. And also see, it is 10 to the power 20. So if you are getting some other power for 10, suppose you are getting 18 or 19, then adjust it. So we have to remove this decimal towards left hand side, and now it will be 2.01. Nearest integer is 2. So the answer is basically 2, not 2 into 10 to the power 20, because you just have to find the value of x. And as we are moving the decimal towards left hand side, 10 to the power 19, it will be now 10 to the power 20. So this is the final answer. It is the number of electrons ejected. 2 into 10 to the power 20. X is 2. Photoelectric effect. So one experiment you have seen, its observation, which is black body radiation, and that you can explain based on particle nature or quantization phenomena. Another experiment which also you can explain only based on this new theory, which is done by Plancks. The second experiment is photoelectric effect, the phenomena of ejection of electron. Now this phenomena you have just seen in this previous problem, right, where we are applying some radiation over the surface of metal and there is ejection of electrons when light of suitable frequency strikes on it. That means not just any frequency of light you can use, there must be some proper frequency. So when it is striking, then only ejection of electron possible. So in the previous problem we have seen, when we are using wavelength 400 nanometer, then only ejection of electron possible. If you are using something else, that is if you are using some energy wavelength, or better say in terms of energy, if you are using some energy lesser than this, ejection of electrons not possible. So there is some minimum value of energy, or you can say particular value of lambda or particular value of frequency. Below of this frequency, ejection of electrons not possible, and these ejected electrons are known as photoelectrons. So in this experiment, there is some detector, because electrons that are coming out from the surface of metal, that we have to detect how many electrons are there, and that we can measure this electricity in terms of ammeter, which basically short form of ampere meter, because ampere is the unit of current. So how much current is produced, that we can measure in this ammeter. Fine. So what are the observations? For each metal, that is what type of metal you have chosen, whether it is sodium or potassium, depending on metal, that is for a particular metal, there is a characteristic minimum frequency, and that is known as threshold frequency. So this minimum frequency you must provide. If you are providing something lesser than this, ejection of electron not possible. So this minimum frequency at least you have to provide. So it is needed to eject the electrons. If it is lesser than this threshold frequency, no ejection of electrons possible, no matter how long it falls on the surface. Suppose you are using some frequency which is lesser than threshold frequency for a very long time. That means how long it falls on the surface. So even if you are continuing the process for a very long time, or if you are doing this with high intensity means frequency is less than threshold, but its intensity is very high. That means number of radiation per second, it is very high. Okay, so that doesn't matter actually. That is how long you are continuing the process, or whether it has very high intensity. Okay, so that is not important. The important thing is whether you are achieving the threshold frequency, then only ejection is possible. Now suppose your frequency that you are providing, it has crossed the threshold frequency, that is there is some excess energy left. So this excess energy will be in the form of kinetic energy. So after ejection of electron, there will be some kinetic energy left that can be used by the ejected electrons. And this excess energy, that is actually directly proportional to the frequency of the incident radiation. So the incident radiation it is such that it is fulfilling obviously the threshold frequency, and even after fulfilling there is something extra, and this extra will be in the form of kinetic energy. Now this kinetic energy, it is also dependent on this frequency of incident radiation, because only if it is exceeding threshold frequency, then only you can get some excess energy in the form of kinetic energy. So kinetic energy is not dependent on intensity, it is independent of intensity. Fine. The number of electrons ejected per second from the metal surface, now that depends upon the intensity. So once the process is started, because you have provided threshold frequency, now after that how many electrons will be ejected, which you can understand from this ammeter, that depends on intensity, okay, or brightness of the incident radiation, but independent of its frequency. So see, ejection of electron, this phenomena will start once you achieve threshold frequency, but how many electrons will be ejected per second, that depends on intensity, that is not dependent on frequency. Fine. So if we explain it in terms of this Planck's concept, which is quantization of energy, all the experimental result could not be explained if you simply follow classical theory, classical physics, according to which the energy content of the beam of light, it depends only on the intensity of light. But energy content is not dependent on the intensity of light. It is dependent on whether particular frequency is reached or not. We have to follow this equation for photoelectric effect. So this is the energy we are providing, and then W is basically work function. So W, you can also express the same equation in this format. So here W is basically, sometimes it is also expressed in phi, and this kinetic energy, this is also the maximum kinetic energy, and this energy is basically h nu, and phi or W that you can express as h nu naught. This nu naught is basically the threshold frequency, and h nu naught or phi or W, it is known as work function. Now if, and this is the nu that you are providing. Now suppose the nu that you are providing, it is equal to threshold. So in that case, what will happen? There will be no energy extra for half mv square, no energy for kinetic energy. Then it will be, you are providing nu 0, this total energy will be utilized for ejection of electron, nothing is left extra. But if there is some extra, because if your frequency that you have used, if it is greater than nu naught, that is nu is greater than nu naught, then only there will be some excess energy left, only if this condition is fulfilled, and we can get maximum kinetic energy, that is possible. So explanation using Planck's quantum theory. Einstein could explain it using Planck's quantum theory, and they are ejected only when incident light has threshold frequency. So it must reach this frequency. If frequency of light, incident light is more than this, some extra energy is there. This excess energy is imparted to electrons in the form of kinetic energy. So h nu minus h nu 0, that will give you maximum kinetic energy. Greater the frequency of incident light, that is higher is the value of this nu, higher will be the kinetic energy, because it is directly related. Greater the intensity of light, number of electrons ejected more. So try to understand this difference. When you are increasing the frequency, basically you can get more kinetic energy, but it has nothing to do with what intensity of light you are using, what is the brightness of light you are using. But if your intensity of light is very high, that means now number of electrons ejected will be very high. But if you cannot achieve the threshold frequency, even if the intensity is very high, ejection of electron not possible. But once it is, the process is starting, because you have applied threshold frequency or you have given something more than this, then ejection of electron possible, and how many electrons will be ejected, that depends on intensity of light. So we are at the end of the session, and thank you for listening.